This is a video tutorial for homework 14 on the conservation of angular momentum. And I'm going to give a few hints for problem number 4, where you have 5 masses which are attached to a rod, and the mass of each of the rod is 0.3 kilograms. And you're told that the length of the rod is 1.07 meters, and the mass of the rod is given to be 2.8 kilograms. And you're told that the whole system is rotating about one end of the rod with an angular velocity of 58 revolutions per minute. So the first thing you have to do is convert the omega in terms of rev per minute to radians per second. So to convert the minutes to seconds, we have 1 minute in 60 seconds. And to convert the revolutions to radians, we have 2 pi radians in 1 revolution. So multiplying this, dividing by 60 seconds gives us the omega in terms of radians per second. And the next thing is to draw the diagram illustrating the problem. So we told that the masses, there's 1 mass at each end of the rod, and the 5 masses are equally spaced. So since they're equally spaced, there will be 1 at this point and 1 at that point. So the other 3 have to be a distance of a quarter of the length of the rod from each other. So the second mass would be located a quarter L from the origin. The third mass would be located a distance of half L from the origin. The fourth mass would be 3/4 L from the origin, and the final mass would be a distance L from the origin. Alright, so we also have to know what the moment of inertia is. So the moment of inertia of the rod is equal to, so since the rod is rotating about one of its ends and not in the center, its moment of inertia will be a third mass of the rod times L squared. And for each of the masses, we can treat them as point particles. So the moment of inertia of each of the mass is equal to the mass of the rod, the mass of the object times the distance from the origin all square. Alright, so we have to find the moment of inertia of each of these masses, and the R here will correspond to the distance of the mass from the origin. Alright, so in the first part of the problem, we have to find the total kinetic energy of the system. So K total will be the kinetic energy of the rod itself, which will simply be half I rod omega square plus the, so I'm just going to use a sum here, where I is equal to 1 to 5. The moment of the kinetic energy of each of the masses attached to the rod. So for each of the masses, we'll have the mass I and the Ri square for the moment of inertia, multiplied by half omega square. And that's because the kinetic energy is equal to half the moment of inertia times omega square, where the moment of inertia of each of the masses is given by its mass times the distance from the origin all square. Alright, so the total kinetic energy just involves breaking up this sum here for all the individual masses. And so we'll have an expression which goes like half I rod is given by a third mass of rod L square times omega square plus, so I'm just going to do for the first two. So the first rod, its moment of the distance is 0, so its kinetic energy is 0. For the second rod, its mass is m, and the distance from the origin is a quarter L. So we have a quarter L all square times half omega square. And then for the third mass, this mass, which is a distance half L, we'll also have its mass times half L squared times half omega squared. And we do the same thing for the fourth mass and the fifth mass to get the total kinetic energy of this system. The second part of the problem asks us to find the total angular momentum. So the angular momentum is equal to the sum of all the objects, including the rod itself, where we are summing over the moment of inertia times the angular velocity. Alright, so in the same way, we just have to repeat the same sum, except that we don't have the half and we are not squaring the omega. So the next clue is for problem number 7, where you have a wheel, a water wheel, with water coming in at some initial speed, 250 meters per second, and then transferring some of its energy into the rotation of the wheel, and then moving out with a speed of 160 meters per second. The numbers could be different for your problem. And we're given the radius of the wheel, R0. And we're told that some mass of the water moves to rotate this wheel, and that's giving us 135 kilograms for each second. Alright, so in the first part of the problem, we actually find the change in the momentum, angular momentum with time. So the amount of angular momentum which is transferred as this water moves from one end to the other end. So the change in the momentum, angular momentum of the water is what it gives rise to the change in angular momentum of the wheel from the conservation of angular momentum. So for the part A, we have to find the L, water, dt. And so this is equivalent to finding the change in the angular momentum of the water divided by the change in time. So this is equal to L final minus L initial. And the change in the time, we're given a change in the mass per unit time, so the change in the time, delta T, is equal to 1 second. Alright, so the L final of the water is given by mv final times the radius. And the L initial of the water is given by mv initial times the radius. And the delta T is 1 second. So putting in these numbers here for the V final and the radius which is given in the problem and the mass of the water moving per unit time, we get the change in the angular momentum of the water with respect to time. So the water is losing angular momentum, so we end up here with a negative sign. But the amount of angular momentum that the wheel gains, so the L wheel dt will be equal to minus the change in angular momentum of the water with respect to time. So since it's gaining angular momentum, we end up with a positive number for the change in angular momentum of the wheel with respect to time.